In this chapter, we'll pivot to talking about game theory. Now, this is obviously a pretty expansive subject, and we'll only be able to do a basic treatment of it in this course, but that should still provide enough of a foundation should you choose to pursue the topic further. We'll start off by talking about how a game is actually defined. So far, we've been looking at problems where individuals are optimizing some objective function subject to a constraint, but always have a solution that is optimal regardless of what other people are doing. However, life isn't so simple. Most of our decisions involve interacting with other people, where the optimal choice depends on predicting what the other person will do. At the same time, they are making their choices based on what they think that you will do. Game theory was developed to address exactly these kinds of strategic interactions and predict what the outcome will be. So to start, we need to define what constitutes a game, which are the players, the strategies, and the payoffs. The players in a game are the participants that are going to make decisions about what actions they're going to take. For our purposes, we're mostly going to focus on two-player games, but we can think about games with any number of players. The strategies are going to represent the choices that players can make. Specifically, we need to distinguish between strategies and actions, as games can present multiple opportunities for a player to act. A proper strategy represents a complete contingent plan and is going to prescribe an action in every conceivable circumstance that the player may face during the game. The payoffs represent the outcomes of the game. And so, depending on the strategies chosen by player 1 and player 2, we're going to have these utility functions that assign a payoff to player 1 and a payoff to player 2. So as you can see here, each player's payoff depends not just on what they themselves choose, but also what the other player chooses. So it's not always possible for each player to individually optimize their choice without considering what their opponent might do. The most well-known game that we study in game theory is the prisoner's dilemma. And this is a famous example of how individuals acting in their own self-interest can produce an outcome that's worse for everyone than if they had just cooperated. Let's imagine that we have two suspects who are accused of the same crime, but the DA doesn't have enough evidence to convict either one of them, and therefore has to try and force a confession from one of them. The suspects are separated, and they're promised leniency if they pin the blame entirely on the other suspect. Now, both of them know that since the DA doesn't have enough evidence, their best bet is just to keep quiet so that neither of them can be convicted. But, as they cannot coordinate their actions, both will have an incentive to betray the other. So we can set this up as a game with two players, each with two possible actions, either keeping quiet or thinking on their partner. This gives us four possible outcomes that we can represent in a matrix form, each of which is going to assign a different payoff to each player. This diagram shows the prisoner's dilemma in normal form, where player 1's actions are the rows and player 2's actions are the columns. If both players stay silent, they're each going to receive a short sentence, getting a payoff of 2 each. If one player stays silent and the other thinks, then the DA concludes that the one who kept quiet must be guilty, and they'll receive the maximum sentence, getting the worst possible payoff of 0, while the other suspect goes free, getting the best outcome of 3. Finally, if both players think on each other, then the DA concludes that they both must be lying, and they're each going to get a longer sentence, receiving a payoff of 1. Notably, the think box is the only one which is unambiguously bad, since both players would be better off at silent instead. In order to solve for the outcome of a game, we need to introduce the concept of a Nash equilibrium. That's defined as the set of strategies where each player is satisfied with their choice and doesn't want to switch to something else. If we let Si be player I's strategy and S minus I be the strategies chosen by everyone else, then we want to think about, is Si a best response to S minus I? And we define that by saying, if the utility that player I gets from playing Si is better than the utility they would get by playing any alternative strategy, then Si is a best response to S minus I. In a Nash equilibrium, each player's strategy is a best response to the strategies played by the rest of the players, which means that no one will want to make a unilateral deviation. If everybody's playing their equilibrium strategies, nobody would want to switch to playing something else, and that defines an equilibrium for this game. Now, importantly, this does not mean that the players couldn't be better off if they made some type of coordinated move. Okay, so Nash equilibrium only addresses a unilateral deviation. But, like the prisoner's dilemma shows, it's difficult in these settings to cooperate sometimes because each player is trying to act in their own interest and they can't force the other players to go along with some kind of coordinated plan. In a two-player game, a Nash equilibrium would just consist of a pair of strategies, S1 star and S2 star. And so we would want S1 to be a best response to S2, and we want S2 to be a best response to S1. So for any alternatives that the players could pick, the Nash equilibrium strategy they're assigned always gives them at least as good of a payoff. If a game has a unique Nash equilibrium, then we can be fairly certain that this is going to be the outcome of the game, because each player will anticipate the other players playing the Nash equilibrium strategy, and they're going to best respond by playing their Nash equilibrium strategy. However, many games have multiple equilibria. So there's multiple sets of strategies that satisfy this sort of condition. And in those cases, it can be pretty difficult to predict what the outcome can be. One thing that we have to keep in mind is that there's no single procedure that we can do that lets us solve for the Nash equilibrium in any game that we're presented with. Instead, there's a variety of methods that we can try for certain types of games, although in some cases all we can really do is guess at what the equilibrium might be and then show that the payoffs are such that no one will want to deviate from it. From the prisoner's dilemma, we can find the Nash equilibrium by just figuring out how each player would best respond to the other player's move. For suspect 1, if suspect 2 finks, then their best response is to fink as well, since it's better to share in the punishment rather than taking all of the blame. If suspect 2 stays silent, then suspect 1's best response is also to fink, because while it might seem like the best outcome if both keep quiet, if suspect 1 finks here, they can get away scot-free and then saddle suspect 2 with all the charges. So in the fink column, we underline player 1's payoff in the fink row. And in the silent column, we also underline the fink row. Because this game is symmetric, suspect 2 has exactly the same payoffs and therefore the same incentives as suspect 1. And their best response is also to play fink for either action that suspect 1 might play. Therefore, in the fink row, we're going to underline suspect 2's payoff in the fink column, and in the silent row, we also underline fink. The Nash equilibrium in this game is the outcome where both players are best responding to each other, being the box where both payoffs are underlined. In the prisoner's dilemma, this means the equilibrium is fink-fink, even though both players would be better off if they moved to silent-silent instead. This is one of the most famous results in game theory, and indeed in all of economics, because it shows that two players, each acting in their own self-interest, can nevertheless produce an outcome that neither of them likes. Both players would like to cooperate and agree to stay silent, but without some kind of binding mechanism to keep them honest, their incentives make this outcome impossible. It's important to note here that the standard version of the prisoner's dilemma is a simultaneous game, and therefore while we talk about best response function, neither player actually has the opportunity to respond to the other one, since both of them make their choices at the same time and the game resolves from there. However, the best response functions allow the players to anticipate how the other player would respond to them, and therefore how they should respond to that, and so on, leading to an equilibrium where both players have chosen a strategy that they won't deviate from, even knowing what the other player is doing. Notably, the prisoner's dilemma is actually pretty easy to solve because for both players, thinking is the optimal choice regardless of what the other suspect plays. And we call that a dominant strategy. Whenever a player has a dominant strategy, all alternative strategies can just be eliminated from consideration, which is really going to simplify the task of solving for the Nash equilibrium. In the prisoner's dilemma, both players know that their opponent has a dominant strategy to think, so we can simply cross out silent altogether because we know that nobody will ever play that. That's going to leave us with just a single box, which gives us the equilibrium outcome, which is fink-fink. Games that have dominant strategies are relatively easy to solve because we can greatly shrink the space of outcomes that we have to consider, and so when analyzing any game, our first task should be to look for dominant strategies. However, in most games, no player has a dominant strategy, and so we're forced to rely on more tedious methods to look for any equilibrium. In the game known as the Battle of the Sexes, we have a husband and wife who are deciding where to go for the evening. Adhering to traditional gender stereotypes, the wife would prefer to watch a ballet, while the husband would rather see a boxing match. But they would both rather be together than apart. Drawing this game in normal form, each player chooses which event to attend separately. The wife is the role player and the husband is the column player. If they choose different actions, both get a payoff of 0 since they're forced to spend the evening alone, whereas if they choose the same action, the winner, that is, the person who goes to the event that they prefer, gets a payoff of 2, and the loser gets a payoff of 1. It's clear that in this game, there's no dominant strategy for either player. Being forced to sit through your less preferred form of entertainment is still better than being alone, at least in the context of this game. And so the best response for both players is to follow where their spouse goes. This gives us two Nash equilibria, ballet, ballet, and boxing, boxing. The fact that there are multiple equilibria makes it difficult to predict what the outcome is going to be. Without introducing any other factors, we're equally likely to end up in either outcome. Now let's think of a game that we've all played, rock, paper, scissors. Here we have two players, each with 3 possible strategies. And as we all know, rock beats scissors, which beats paper, which beats rock. If we draw this game in normal form, in each box, if the players choose different actions, then the winner gets 1 and the loser gets -1. While if they choose the same action, they're going to tie, so both get 0. If we try the underlying procedure, we see that the best response to each player is to pick the move that will win the game. So if they choose rock, you choose paper. If they choose paper, you choose scissors. And if they choose scissors, you choose rock. Therefore, no matter which box we look at, there's always going to be at least one player with an incentive to deviate, because there's always a strategy that would make them the winner. And so far as we can tell, therefore, there's no Nash equilibrium in this game. There's no equilibrium where both players are satisfied with their choice. One important result in game theory, though, is that every game has at least one Nash equilibrium. Even games like rock, paper, scissors that don't seem to have one. The disconnect here is that so far we've only considered pure strategies. So those are strategies where a player chooses a particular course of action with certainty. And as we've seen from this example, not every game necessarily has a Nash equilibrium in pure strategies. A mixed strategy, on the other hand, is going to see a player randomizing between a number of pure strategies. And in games like rock, paper, scissors, the only way that you can really win is to play unpredictably so that your opponent can't just choose the optimal counter strategy. Now, while it's questionable whether anybody can truly randomize without revealing some kind of pattern that their opponents can pick up on, let's just assume for now that the players have some mechanism by which they can randomly select among a set of strategies with predefined probability weights. A mixed strategy is defined as a set of probabilities sigma I1 through sigma IM that correspond to pure strategies AI1 through AIM. And so sigma I1 is going to be the probability of choosing pure strategy AI1. And so all of the sigmas are going to add up to 1. So for example, in the Battle of the Sexes game, the two pure strategies, A1 and A2 for both players, are ballet and boxing. And so a mixed strategy we can write as sigma and 1 minus sigma. So sigma is the probability that you go to the ballet, 1 minus sigma is the probability you go to the boxing match. In order to solve for a mixed strategy equilibrium, we have to think about under what conditions would someone actually play a mixed strategy? When would someone want to randomize? So, given the strategy chosen by your opponent, a player might have multiple best responses that would yield the same payoff, and therefore they would be indifferent between each of these strategies, or indeed between any mixture of these strategies. Because they have to necessarily view all of the actions that they're randomizing over to be equivalent, there's no optimal probability weights. If you get the same payoff from playing ballet or boxing, it doesn't matter what probabilities you choose. You get the same payoff from any mixed strategy. Instead, if we know that we're solving for an equilibrium where both players are playing mixed strategies, then one player's probabilities will be chosen so as to induce the other player to mix by making them indifferent between these pure strategies, so they'll play a mixed strategy, and vice versa. For example, let's suppose the wife plays a mixed strategy 1/9, 8/9. So she goes to the ballet with probability 1/9, and the husband plays a mixed strategy 4/5, 1/5. So he goes to the ballet with probability 4/5. So let's think about all of the possible outcomes. There's a 4 out of 45 chance that they both go to the ballet. Here, the wife is going to get a payoff of 2, and the husband will get a payoff of 1. There's an 8 out of 45 chance that they both end up at the boxing match. In this case, the wife is going to get a payoff of 1, and the husband is going to get a payoff of 2. There's a 1 out of 45 chance that the wife goes to the ballet, and the husband goes to the boxing match. In this case, both players would get a payoff of 0. And finally, there's a 32 out of 45 chance that the wife goes to the boxing match and the husband goes to the ballet. Here, they would both get 0 again. So if we calculate the expected payoffs, the expected payoff to the wife is going to be 16 over 45, and to the husband, it's going to be 4/9. In general, if the wife plays a mixed strategy W1 minus W, so W is the probability the wife goes to the ballet, and the husband plays H1 minus H, then they're both going to end up at the ballet together with probability WH, and they're both going to end up at the boxing match with probability 1 minus W, 1 minus H. So the wife's expected payoff, she's going to get 2 here and 1 here, which gives us 1 minus H minus W plus 3 WH. So what the wife is going to do, she's going to choose W to maximize this expected payoff. So what's she going to do? If H is less than 1/3, she should pick W equals 0. Why? In this case, her husband is more than likely going to go to the boxing match, so she's better off just following him there. If H is greater than 1/3, then she should pick W equals 1, because in this case, he's sufficiently willing to go to the ballet that she's better off just going there too. If H is exactly equal to 1/3, then any value of W is a best response, because if we plug in 1/3 here, what we see is that she gets the same payoff no matter what. What that means is that the only case where the wife would play a mixed strategy is if H is equal to 1/3. And when she does play a mixed strategy, her payoff does not actually depend on the mixed strategy she chooses. If H is equal to 1/3, then the wife is going to get the same payoff no matter what value of W she plays. For the husband, he gets 1 from going to the ballet with his wife and 2 from going to the boxing match. So his expected payoff is going to be 2 minus 2H minus 2W plus 3 WH. Just like his wife, he's going to try and follow his spouse where he thinks she's more likely to go. If W is less than 2/3, then he should pick H equals 0. If W is greater than 2/3, he should pick H equals 1. And if W is exactly equal to 2/3, any value of H will maximize his expected payoff. Once again, he's only going to play a mixed strategy for a specific value of W, and if he does, the value of H that he plays doesn't affect him. If we plot the best response functions on the same graph, we can see here that there's going to be 3 different Nash equilibria for this game in mixed strategies. By definition, a Nash equilibrium exists anywhere where both players' choices are best responses to the other player. So we have the 2 pure strategy equilibria where W and H are both 0. In that case, they both go to the boxing match. And when W and H are both 1, so both go to the ballet. However, we also have a mixed strategy equilibrium where W equals 2/3 and H equals 1/3. And note that these probabilities are not chosen because they're somehow optimal for the player that's choosing them, but because they're exactly the values that would make the other player indifferent and therefore willing to play a mixed strategy. If they had chosen any other probabilities, one or both would have had an incentive to deviate by shifting all their weight to a pure strategy, and so there could be no other mixed strategy equilibrium. Nash proved that every game has at least one Nash equilibrium in mixed strategies, but not necessarily in pure strategies. However, don't let this fool you into thinking that we can just repeat the procedure we just used for the Battle of the Sexes game, since in many games there isn't a finite space of possible actions, but rather a continuum, so an infinite number of choices you can make. For example, 2 firms competing in the same industry may simultaneously be choosing the quantity that they want to produce. In a game like this, we will have to use first order conditions to derive the best response function for each player, and then solve a system of equations to find the Nash equilibrium. The tragedy of the commons is a parable showing how resources shared in common will invariably be overexploited. So let's suppose that we have a plot of pasture land that two herders can use to graze sheep. However, the more sheep there are grazing on the same grass, the less that each individual sheep can eat, and therefore the less value the herder can derive from each one. Specifically, we're going to let the value of each sheep be 120 minus the total number of sheep. So Q1 is the number of sheep of herder 1, Q2 is the number of sheep from herder 2, and so the value of each sheep is diminished with each additional sheep. Crucially, some of the cost of overgrazing is pushed onto the other player. So if you bring too many sheep, your sheep will not grow as fat, but the same will be true of theirs. What that means is that both players here have an incentive to overgraze, which leads to the tragedy. Because some of the costs, some of the consequences of your action are felt by the other person. So the payoff to player 1 is going to be Q1 times the value per sheep, and the payoff to player 2 is going to be Q2 times this expression. To solve for herder 1's best response function, we maximize their payoff with respect to Q1. So we get 120 minus 2Q1 minus Q2 is equal to 0, or Q1 is 60 minus Q2 over 2. Now by symmetry, player 2 has the same best response function. So 60 minus Q1 over 2. To solve for this equilibrium, we can plug this expression for Q2 in for Q2 up here. So we're going to have Q1 is 60 minus Q1 over 2, or 30 plus Q1 over 4. If we solve for this, we get that the optimal number of sheep for player 1 is 40, and we plug this into player 2's best response, we get that Q2 star is also equal to 40. Each player bringing 40 sheep means that the value of each sheep will be 40. So the payoff to player 1 is 1600, and the payoff to player 2 is also 1600. However, just like in the prisoner's dilemma, this equilibrium is going to make both players worse off than if they had found a way to cooperate. Because let's consider instead an alternative where both players only bring 30 sheep. Then in that case, each sheep would be worth 60, and so both players would get a payoff of 1800, which is better than the 1600 they get in this Nash equilibrium. So we can see that in the tragedy of the commons, both players have an incentive to overgraze, which makes them both worse off than if they had arrived at some cooperative solution. This diagram plots the best response functions of the two players, indicating each player is going to reduce the number of sheep they graze when the other player increases theirs. The intersection of the two lines is a Nash equilibrium E1. If the value per sheep increases, but only for player 1, then their best response function is going to shift out. That gives us a new asymmetric equilibrium E2, where Q1 has increased, but Q2 has decreased. So player 1, their sheep are more valuable, they're going to bring more to the pasture and crowd out player 2. So far, we focused on simultaneous games, so both players are acting at the same time without observing what the other player is doing. However, we can also consider sequential games. In this case, one player moves first, and then the second player observes what the first player is doing and then moves. So they can choose different plays depending on what they observe the first player doing. Let's look at a variant of the Battle of the Sexes game where the wife moves first. Once again, she has two possible strategies: go to the ballet or go to the boxing match. The husband moves second, and therefore he can condition his action on what he observes his wife doing. So a strategy for him is going to comprise a complete contingent plan, which specifies one action if he observes her playing ballet, and another, possibly a different action, if he observes her playing boxing. With two possible choices at each of these decision nodes, he therefore has four distinct strategies. He can go to the ballet no matter what, he can go to the boxing match no matter what, he can copy whatever he sees his wife doing, or he can always do the opposite of what she does. If we draw the matrix for this game, we have to now account for the fact that since the husband has four separate strategies, there's 8 boxes to fill. Now, the husband's strategy specifies an action conditional on either possible action the wife may take. But you can see that only one of these choices is actually relevant in determining the payoff. In the first row, when the wife is playing ballet, only the first of the husband's choices matters when resolving the outcome. In the second row, where the wife is playing boxing, only the husband's second choice matters. As we see here, the normal form for sequential games can quickly get out of hand when adding more moves and more decision nodes. So this is really not the preferred way of illustrating them. In this diagram, we have the Battle of the Sexes game drawn in extensive form. Player 1 is the wife and she chooses her action first, and then player 2, the husband, chooses his action. Because he can observe what she chooses and condition his action on that decision, he has 2 decision nodes. One at the top, which is conditional on her playing ballet, and the other at the bottom, which is conditional on her playing boxing. We can also draw the simultaneous version of the game in extensive form, but we have to modify it by connecting the husband's 2 decision nodes in one information set. What this information set means is that the husband doesn't know which of the nodes within the information set he is at, and so therefore he's forced to choose the same action at both. Now, this technically describes a game where the wife still does move first, but the husband just can't see what his wife is doing, and so therefore can't condition his move on hers. But if you think about it, this is actually going to produce identical results to the simultaneous game, because it makes no difference whether they move at the same time or whether one player moves first but the second player just can't see what the first player is doing. So we can use the tree to represent either the simultaneous game or the sequential game where the second player can't observe the first player's action. In game theoretic terms, they're equivalent. We can find the Nash equilibria of the sequential game by using the underlying procedure. So here I've reproduced a normal form, and just for the sake of simplicity, A represents ballet and O represents boxing. So here are the wife's 2 strategies, and here are the husband's 4 strategies. So if we're looking at the wife's best response, going from left to right, she's going to go up, up. Either up or down are okay here, and down here. For the husband, he's in the first row going to either pick this one or this one, and in the second row, he's going to pick this one or this one. This means we have 3 Nash equilibria in this game. In the first one, both players go to the ballet no matter what. In the second one, the husband is always going to follow what his wife does, and so the wife, knowing this, will always choose ballet. Now in the third one, this one's kind of interesting. The husband chooses boxing no matter what, and the wife is forced to go to the boxing match. Of these three equilibria, you can see that two of them favor the wife. She's going to get a better outcome than her husband. And only one of them favors the husband. And actually, this last equilibrium is pretty weak because it relies on the husband making a threat to go to the boxing match no matter what, which forces his wife to choose to go there also. What this tells us is that in this particular game, the first player, which is the wife, has the advantage. To show why this is true, we need to introduce a refinement of the Nash equilibrium concept known as the subgame perfect Nash equilibrium. To do that, we need to first define what a subgame is. So a subgame is any branch of the game tree that includes a node and all of its children. So a subgame can define a game in its own right that we can then solve. A subgame perfect Nash equilibrium is a Nash equilibrium that's also an equilibrium in every subgame. And the reason that this is significant is that it rules out the possibility of empty threats. Another benefit of this restriction is that subgame perfect equilibria can be solved much more easily using backward induction. Starting from the last move, we can find the equilibrium strategies in each subgame and then work backwards, allowing players to anticipate what the next move is going to be given the solutions that we've already obtained. In the Battle of the Sexes game, the only way that the husband can get his way is if he threatens to play boxing no matter what, declaring that even if his wife is going to the ballet, he'd rather be by himself than see his masculinity threatened. Of course, this isn't actually the case, since if she were to call his bluff and play ballet anyway, he would get a better payoff from following her. So as long as she doesn't call his bluff, and this particular choice remains off the equilibrium path, then it has no influence on the final payoffs, and so neither player has an incentive to deviate, as a Nash equilibrium requires both players to take the other at their word and not anticipate any reactions to a potential deviation. So, in this particular case, while the wife might be pretty confident that if she were to switch her choice from boxing to ballet, that the husband would do the same, if she holds his strategy fixed, she has no incentive to deviate. And if he holds her strategy fixed, he also has no incentive to deviate. And so this does remain a Nash equilibrium, but not a terribly compelling one. It relies on an empty threat. To find the subgame perfect Nash equilibrium, we need to first find all the subgames. In the sequential version of the game, we have three. The upper branch that resolves only if the wife plays ballet, so that's at B. We have the lower branch if she plays boxing, starting at C. And then the entire game is also a subgame. In the simultaneous version of the game, because the two branches are connected by an information set, they can't be separated. So the only subgame is the entire game, which we label as D. We can now use a backward induction to solve for the equilibrium. At the upper node, we have a subgame that involves only one player, the husband, who he's obviously better choosing ballet here. While at the lower node, we have another one-player game where the equilibrium is the husband choosing boxing. We're now going to collapse these subgames because the wife can anticipate what the husband will do in response to her moves. Her choice just boils down to picking her favorite event, knowing that her husband will inevitably follow her wherever she goes. So she's going to choose ballet. This means that the unique subgame perfect Nash equilibrium sees the wife playing ballet while the husband plays ballet on the upper node and boxing on the lower node. This is an equilibrium in every subgame, so it involves no bluffs, and each player's choices are going to be optimal even off the equilibrium path. Now, the conclusions from the Prisoner's Dilemma and other similar games might seem pretty grim, because they seem to imply that people are always going to behave in selfish and self-defeating ways instead of just cooperating for mutual benefit. However, that's because so far we've only considered one-shot games, so the players interact once and never interact again. If games are repeated, however, that opens up the possibility for cooperation based on a pattern of past behavior that builds credibility. Now, this isn't the case for every game. Any repeated game, there is a Nash equilibrium that just repeats the equilibrium in the one-shot game in each round. In a game with multiple equilibria, like Battle of the Sexes, the players may cooperate by, say, agreeing to alternate the outcome each round. So you go to the ballet one week and you go to the boxing match the next week. However, what we're really most interested in are games where a cooperative outcome can be sustained in a repeated context that wouldn't be possible in a one-shot game. In the prisoner's dilemma, we can sustain a cooperative equilibrium if both players adopt what's called the Grimm trigger strategy. And what that means is that each player is going to stay silent if you observe the other player staying silent. But once you observe the other player thinking, then you're going to switch to think forever with no possibility of going back to cooperation. If we're both cooperating, we're getting a payoff of 2 in every round. If one player were to deviate, then you would get a payoff of 3, but only in the first round, because afterwards that would set off the Grimm trigger strategy and we would be back at the one-shot Nash equilibrium, which gives us a payoff of 1 in each round. So what you can see here is that the incentive to deviate doesn't look as obvious now, because rather than just getting 3 over 2, you're trading an infinite sequence of getting 2 every round versus a one-time payoff of 3 followed by the payoff going down to 1 every round afterwards. Let's say that the payoffs are discounted at a rate of delta. So every unit of utility is worth 1 here, and delta here, and delta squared here, and delta cubed here, and so on. So the payoff to cooperating is 2 plus 2 delta plus 2 delta squared, and so on. And since this forms a power series, it's going to converge to 2 over 1 minus delta. The payoff from deviating is going to be 3 plus delta squared. And this is going to give us 3 plus delta over 1 minus delta. It's going to be 3 plus the sum of this series. So in order for silent to be the better choice, in order to keep cooperating, we need this to be higher than this. So if we multiply both sides by 1 minus delta, we're going to get that we need 2 to be greater than or equal to 3 times 1 minus delta plus delta, or 3 minus 2 delta. And so the condition that we need to sustain cooperation is that delta has to be at least 1/2. What that means is that my discount rate has to be high enough where I value the future enough so that the losses from deviating outweigh the gains. I need to care enough about the future in order to keep cooperating. If delta is too small, then it's still going to be better for me to deviate. In the Grimm trigger strategy, the players are going to choose the harshest possible punishment with no possibility of ever returning to cooperation, even after just one case of deviating. This is because they want to provide the strongest possible disincentive. However, in practice, we rarely observe these types of strategies since people tend to be more forgiving. For example, you might impose a punishment of deviating, but only for a fixed number of rounds. and afterwards you're open to returning to cooperation. Now, while a strategy where we only impose a lighter punishment might seem less harsh and more forgiving, and so it's easier to sustain more cooperation, it's also going to serve as less of a deterrent. There's less disincentive to deviate, so your opponent has more opportunities to exploit it. So far, we've only considered games where both players have full information about the choices available to the other players and what payoffs they might receive in each outcome. However, in reality, this is often far from clear. Players struggle to discern the motives and incentives of their opponents. Let's say we have a game where one player has private information about themselves that's unknown to the other player. And the different types of player 1 will behave differently, and player 2 has to choose their strategy based on their beliefs about the probability that player 1 takes each type. So let's say that player 1's type, TK, is chosen from a range of possible types, and this can only be observed by player 1 but not by player 2. Therefore, player 1's type is going to influence the payoffs both directly and indirectly through the choices that player 1 makes. Let's look at a simple game where player 1 chooses up or down and player 2 chooses left or right. The payoffs for 3 of these outcomes are fixed, but the up-left box depends on player 1's type. So T can either be 0 or 6. Now, type has no direct impact on player 2's payoffs, but it does have an indirect effect through player 1's strategy, which possibly yields different outcomes depending on the value of T. So let's first imagine that T were known to both players. If T is equal to 0, then down is a dominant strategy for player 1. So player 2 would respond by playing right. So down right is the Nash equilibrium. If T is equal to 6, both up left and down right are Nash equilibria, as in either of these cases, neither player would want to deviate. To model the game with incomplete information, we imagine that there's a third player called nature that randomly determines the type of player 1 before either player moves. Player 2 can neither observe player 1's move or their type. So all 4 nodes are combined to a single information set. Player 2 only has the chance to make a single move. Player 1 has 2 decision nodes, and so each type of player 1 can choose a different move. In a Bayesian-Nash equilibrium, each player has to choose not only a strategy, but beliefs that support that choice. Player 1 knows their type with certainty, so they have to choose a strategy for each value of T that maximizes their payoff, while player 2 only gets to choose a single strategy that maximizes their expected payoff. So for each type of player 1, the equilibrium strategy, which also depends on T, gives a higher payoff than any alternative. Whereas for player 2, if I sum up the probability of each type times the payoff to player 2, then that's better than the expected payoff that player 2 gets from playing any alternative strategy. Let's try to find a Bayesian-Nash equilibrium in this game where I've reproduced the normal form here. Now let's consider 2 candidates. One where player 2 is going to play left, and another one where player 2 is going to play right. If player 2 chooses left, then if t is equal to 6, player 1 is going to play up. And if t is equal to 0, they're going to play down. This means that player 2 gets a payoff of 2 with probability 1/2 and a payoff of 0 with probability 1/2. So they get an expected payoff of 1. However, if player 2 were to choose right instead, they would get 0 with probability 1/2 and 4 with probability 1/2. They would get an expected payoff of 2. So they would prefer to deviate to right. So this can't be a Nash equilibrium. If we look at the candidate where player 2 is playing right, then both types of player 1 would choose down, because now the type doesn't matter. So down if t is equal to 6, down if t is equal to 0. And if we look at player 2's incentives, they would get 0 from playing left, so they don't want to do that. So this is in fact a Nash equilibrium. Now, remember that if we had full information, up left could potentially be a Nash equilibrium if t is equal to 6. But with incomplete information, this is no longer a possibility. The only Nash equilibrium with asymmetric information is down right. Now, let's return to the tragedy of the commons game, but with the modification that the value per sheep for player 1, instead of starting at 120, instead depends on some unknown type t, and t can either be 130 with probability 2/3 or 100 with probability 1/3. The payoff function for player 1 is going to be Q1 times the value per sheep. So if we maximize this, we get that player 1's best response function is going to be t minus Q2 over 2. So for the high type, that's going to be 65 minus Q2 over 2. And for the low type, that's going to be 50 minus Q2 over 2. Now, player 1's type has no direct impact on player 2's payoff, but player 2 will anticipate that each type of player 1 may choose a different quantity. So player 2's baseline value is 120 per sheep. But with probability 2/3, player 1 is going to be of the high type and play Q1H. And with probability 1/3, player 1 is going to be of low type and they're going to play Q1L. So player 2's payoff is going to depend on the average quantity played by player 1, where Q1 bar is 2/3 Q1H plus 1/3 Q1L. And if we plug in these expressions, that's going to average out to the same 60 minus Q2 over 2 that we had in the standard version of this game. If we maximize this thing, player 2's best response is 60 minus Q1 bar over 2. And so that we get that Q2 star is just like it was in the full information game. Q2 star is going to be 40. But if we plug this into player 1's best responses, we get different numbers. So we're going to have that Q1H star is 45 and Q1L star is going to be 30. So one thing that we should note here is that these are not the same quantities that the players would choose if player 1's type was known. If player 1 was always high type, so Q1H once again was 65 minus Q2 over 2, Then Q2 would be 60 minus Q1H over 2, or 55 over 2 plus Q2 over 4. And that's going to give us Q2 star is 110 over 3, and Q1H star is going to be 140 over 3. If player 1 was always low type, so remember Q1L was 50 minus Q2 over 2, Q2 would be 60 minus Q1L over 2, or 35 plus Q2 over 4. That would give us Q2 star equals 140 over 3, and Q1L star is equal to 80 over 3. So, once again, these are the Nash equilibrium quantities when the type of player 1 is unknown, and they don't match what the Nash equilibrium quantities are when the type of player 1 is known. So this would not be a Nash equilibrium if player 2 knew that player 1 was high type, and this would not be a Nash equilibrium if player 2 knew that player 1 was low type. This diagram shows that in this equilibrium, player 2 responds to the expected best response of player 1, which is given by the dashed line. So the outcome is going to be at point C with probability 2/3. That's if player 1 is actually high type, and at point A with probability 1/3. That's if player 1 is actually low type. And these outcomes average out to point B. If player 2 actually knew what player 1's type was with certainty, then the Nash equilibrium would either be at point C prime if they knew that player 1 was high type, or at A prime if they knew that player 1 was low type. So far, we've looked at games where, yes, player 1's type is unknown, but player 2 is just going to maintain some fixed beliefs about what player 1's type could be. In sequential games, however, player 1 can use their action to signal something about their type to player 2, which would then cause player 2 to update their beliefs. So, depending on the game, player 1's optimal strategy may not necessarily be to behave truthfully. They may have an incentive to purposely send a deceptive signal to induce a favorable response from player 2. Let's consider a job market signaling game where player 1 is a candidate and player 2 is the firm, and player 1's type can either be high skill or low skill, and player 2 decides whether they want to hire player 1 or not. If player 1 is high skill, they generate a revenue of pi for the firm and are paid a wage of W, so the firm's profit is pi minus W. But if they're low skilled, they don't generate any revenue, so the firm just loses W. We're going to assume that pi is greater than W is greater than 0, so that the firm will only want to hire a candidate if they think there's a reasonably good chance of being high skilled. Now, how is the firm going to determine what the candidate's type is? Now, they could just ask them, but if somebody asked you whether you were skilled or not, you would always say yes. Why? Well, because there's no cost to lying, but there's a potential gain if you get hired for a job. So we can't have the candidate signaling their type without introducing some type of a cost. We don't want the low type to falsely portray themselves as high type, so we need to have a big enough penalty for both types to tell the truth. So how would we do something like this? Well, one such mechanism is education. Now here, education level doesn't impact productivity at all. Productivity is only determined by type. However, education is useful here because it's a costly signal, And the cost to send this signal is lower for the high type than for the low type. So, education has no impact on job performance, but it's cheaper and easier for a highly skilled worker to obtain it. And so, if a worker holds a degree, that could potentially send a strong signal to a potential employer that they're highly skilled and therefore influence the firm's hiring decision. If we look at the tree for this game, the first move sees nature selecting the type. And then player 1, the worker, chooses whether to seek education, E, or not, NE. Player 2 can observe player 1's action, but not their type, and so has two information sets. One conditional on E, that means they observe a candidate who has education, and one conditional on NE, which means that they observe a candidate without education. Then, in each information set, player 2 can either choose to offer the candidate a job, J, or not, NJ. If we look at the payoffs, we see that W, the wage, is transferred from player 2 to player 1 if and only if J is chosen. On the other hand, player 2 receives a revenue of pi only if the worker is high type. So here, education has no impact on player 2's payoff, but it incurs a cost of CH for the high type and CL for the low type. The difference between this particular game and the ones that we've looked at before is that player 2 has a chance to observe player 1's action, and upon observing their action, can update their beliefs about player 1's type. What that means is that player 2's payoff doesn't depend on the unconditional probability of player 1 being high type, but rather the conditional probability upon observing either that they got an education or that they didn't. So if the firm observes a candidate that is educated, then with probability H given E, they get a payoff of pi minus W, and with probability L given E, they get a payoff of minus W. Whereas if they observed the candidate that did not get education, these would just be replaced with the conditional probabilities given no education. In a Bayesian-Nash equilibrium, these posterior probabilities have to be formed via Bayesian updating. So the posterior probability H given E has to depend on the relative likelihood of choosing E given either type. So if we use Bayes' rule, we get that the probability of H given E is given by all this. And likewise, if we want to find the probability of H given NE, we just replace E with NE in each of these terms. Therefore, we can think of Bayes' rule as a black box. We're going to take player 2's prior beliefs, that's the probability of H unconditional on player 1's action, and we're going to take player 1's action as the other input, and this black box is going to spit out player 2's posterior beliefs. Now, the formula for Bayes' rule looks a lot more complicated than it really is. And if we restrict player 1 to pure strategies, the expressions get pretty simple. Let's imagine that player 1 plays a pure strategy where they only get education if they're high type. Then, the probability of observing a high type, given that you saw education, is going to be 1 times the probability of H over 1 times the probability of H plus 0 times the probability of L, which is just going to be 1. This means that education is a perfect signal of type. Here, only high types get education, so if I observe a worker with education, I automatically know that they're high type. Let's consider another possibility. Let's suppose that both types are always going to choose education. Then, plugging in those numbers into Bayes' rule, I get that the conditional probability of high type is just going to be equal to the unconditional probability. This means that this signal is not informative. The posterior probability is not updated from the prior. More generally, we can think about player one playing a mixed strategy. So they're going to choose education with probability P if they're high type, and probability Q if they're low type. And that means the posterior beliefs are going to be P times the unconditional probability of H over this plus Q times the unconditional probability of L. A perfect Bayesian equilibrium in this game consists of strategies as well as beliefs for each player. The strategies will maximize expected payoffs given the beliefs, while the beliefs are consistent with Bayes' rule if we plug in the probabilities specified by the strategies. We can divide the possible equilibria into three categories. In a separating equilibrium, each type of player one chooses a different action. That's going to reveal this information to player two. In a pooling equilibrium, each type chooses the same action, so player two learns nothing. A hybrid equilibrium is somewhere between these two cases, where maybe one type plays a mixed strategy and the other plays a pure strategy. This means that the signal is informative, but only partially so, and it might induce player two to also choose a mixed strategy. Let's think about a separating equilibrium where the high type always chooses education and the low type never does. This is going to perfectly signal to the firm how skilled the worker is. So the firm's posterior beliefs are that the probability of high type given education is 1, and that the probability of a high type given no education is 0. Given these beliefs, the firm gets a payoff of pi minus w if they hire here, so they'll pick J, whereas they know they'll get a payoff of minus w here, so they'll pick NJ. That means the firm will always offer a job if they see education and never offer a job if they don't. To check that this is in fact an equilibrium, we also have to make sure that it's incentive compatible for the worker. Now each type gets W minus C if they get hired and 0 if they don't. And we need these costs to be such that it's worthwhile for a high type to get education, but not worthwhile for a low type. That is, the cost of getting education for the low type is so high that they would rather just honestly signal that they're low type rather than pretend to be high type. This means that we need W to be between CH and CL so that both types have the right incentives. Now let's consider a pooling equilibrium. So let's look at a pooling equilibrium where both types always get education. If a firm observes an educated worker, their payoff is going to be probability of H given E times pi minus W. And because both types always get education, the unconditional probability equals the conditional probability. So they're going to hire as long as the unconditional probability of H is greater than W over pi. However, we also have to think about what happens if the firm encounters a worker without education. Now, this is actually off the equilibrium path in this case because both types of worker will get education, So the firm will never actually observe someone who doesn't. However, the firm's choice in this hypothetical situation, which once again is off the equilibrium path, is still going to matter. Why? If the firm hires workers even without education, then it won't be worthwhile for the workers to get education because they'll get hired no matter what. Therefore, as part of this equilibrium, the firm's beliefs given observing no education have to be such that they don't hire anybody without education. This means that we need W over pi to be greater than the probability of H given NE. Now, if we were to expand this guy using Bayes' rule, we would get probability of NE given H times the probability of H over this plus the probability of NE given L times the probability of L. Now, here, this is 0, this is 0, and this is 0. So this probability, if we use Bayes' rule, is just going to be 0 over 0, which is an indeterminate form. What that means is that because this particular event is off the equilibrium path, Bayes' rule is not going to give us an answer. So, in a Bayesian equilibrium, a player's beliefs off the equilibrium path can be whatever they want. However, in order to sustain this particular equilibrium, this pooling equilibrium where both types choose education, the firm must arbitrarily set their beliefs off the equilibrium path such that they're low enough to avoid hiring anybody without education. Remember, this is off the equilibrium path because everybody is educated in this case. So their beliefs here are not going to be justified by what they observe, but they still need to be low enough so that they choose NJ in this case, which will then in turn give the workers the incentive to choose E. Finally, let's consider a hybrid equilibrium where the high type is always going to get an education, but the low type is only going to do so with probability E. The firm is going to respond by itself playing a mixed strategy. So the probability of hiring given E is going to be equal to J. And they're not going to hire any uneducated applicants. Now, just like in the battle of the sexes example, we're going to choose these probabilities, E and J, in order to make the other player indifferent. By Bayes' rule, the probability of H given E is going to be 1 times the probability of H over this plus E times 1 minus the probability of H. In order to make the firm indifferent, we need this times pi minus W to be equal to 0. So they're indifferent between hiring and not hiring. So if we plug this in here, we get pi times the probability of H is equal to W times the probability of H plus E times 1 minus the probability of H. And if we solve there, we get E star is equal to pi minus W times the probability of H over W times 1 minus the probability of H. Now for the worker, we need J times W, J is the probability of getting hired, minus CL to be equal to 0. So the low type is indifferent between getting education and not. So we get J star is equal to CL over W. This would also mean that J star times W minus CH is strictly greater than 0. So it will always be better for the high type to get educated. They're not mixing. Therefore, the hybrid equilibrium can be supported whenever CH is less than CL is less than W. Now, remember that a separating equilibrium required this. So if W is higher than CL, then we can get a hybrid equilibrium. If W is between CH and CL, we can get a separating equilibrium. We'll end this chapter by noting that the results predicted by game theory don't always line up with how we observe people to actually behave when we put them in an experimental setting. Broadly speaking, subjects tend to behave more altruistically at first, but repeated play tends to converge toward this kind of self-interested behavior that we see in the prisoner's dilemma. There's a couple ways that we can explain this. One is that our behavior isn't necessarily dictated by rational self-interest, but it's rather hard-coded inside us. And so through some kind of evolutionary process, some optimization takes place where players who are endowed with more beneficial behavioral patterns will survive. Thus, even if cooperation didn't serve immediate interests, tribes that were able to cooperate would eventually outlive those that acted selfishly and ended up killing each other off. And so a sense of altruism became ingrained within us simply because those that didn't see the world this way died off. Alternatively, rather than being hard-coded, behavior can be learned through experience. And so players who have benefited from cooperation in the past will be more likely to cooperate in the future, compared to those who have been backstabbed often and learned not to trust anyone. In this case, players would behave more like what game theoretic models would prescribe, but with beliefs shaped by their experiences rather than calculated by the rules that we've just laid out.